Alright, this particular example is one that we worked in class. It's also one that is relevant to your project, so I know you're probably mostly familiar with how to do this. But we'll go back over it and I'll make a few comments. So basically here we're considering a TE10 wave at 10 gigahertz in a copper rectangular waveguide. The A and B dimensions are given here. We're told that it's filled with polyethylene. We're given the epsilon prime for polyethylene, which is 2.25, and we're given sigma for copper, which is 5.8 times 10 to the 7th Siemens per meter. And then we're also given the loss tangent, 4 times 10 to the minus 4th, at 10 gigahertz. So we're asked to find the various parameters, and the first thing I want to address is this topic of the loss tangent. So the loss tangent is basically doesn't change much with frequency until you get above 10 gigahertz, and it's an experimentally determined parameter, and polyethylene can change quite a lot. So typically you do have to be given this, or you have to go to the literature or some other resource to find it. And I'll just show you briefly what I found in a publication. If we look at this publication here, posted on ResearchGate, it gives several parameters of polyethylene, and right here we have the loss tangent. So you can see if we were to come to 10, we look pretty close to 0, really, because this is such a poor scale, and we don't really have a lot of tick marks here. We can't really tell that that would be 0.04. But I wanted to show you this so that you can see the behavior. This is a logarithmic scale here, so 2 or 20 gigahertz would appear somewhere over here, which gets our loss tangent up quite a bit higher, probably at about 0.05. So in this particular experiment, we see quite a bit of change between 10 gigahertz and 20 gigahertz in the loss tangent. So anyway, that's just an aside because I did get several questions on that. So generally the loss tangent would be something that you would have to be given, and it does enter into these formulas, especially when calculating dielectric losses. So we're asked first of all to find these parameters in the guide for this particular mode, and then we're asked to find the losses due to conductivity and due to the dielectric. So the first thing we have to do is we have to calculate the parameters outside the guide. So the phase velocity, given polyethylene, the phase velocity is roughly c over the square root of the relative dielectric constant. Now we have the approximate here because this is a low loss dielectric, and so we're basically assuming that the lossiness of the dielectric does not affect the phase velocity. On the other hand, it will affect some other parameters. So calculating the phase velocity, we get 2 times 10 to the 8th meters per second, and then from that and the frequency, we can then get lambda. So now we can calculate the cutoff frequency, which is Vp, the phase velocity, over 2a. So we take our 2 times 10 to the 8th, we divide by 2 times the guide dimension, and we get 5.25 gigahertz as a cutoff frequency. Now the reason it's important to calculate the cutoff frequency is that it shows up in all the formulas to find the parameters in the guide. So that would be given here, and you can see the cutoff frequencies are shown in these formulas. And by the way, fine to use omega here, as long as both are omega or both are hertz. It doesn't really matter because the units are going to cancel out in this ratio. So this is a unitless ratio. So to find beta in the guide, we take normal beta, which would be omega over phase velocity, and we multiply by this guide factor. To find lambda in the guide, we take normal lambda, which would be lambda outside of the guide, and we divide by the guide factor. And then to find normal phase velocity, we take phase velocity outside of the guide, and we divide by the guide factor. So that's just sort of the approach you take in order to find the things in the guide. Now that we have that, we can look at determining the surface resistance of copper. At 10 gigahertz, it's given by the following formula. And so plugging in all of the relevant pieces of information, we get 2.61 times 10 to the minus 2 ohms. And so that would be basically the surface resistance at 2 gigahertz. So next, We calculate the conductive losses. So we have this surface resistance, and then we have these parameters that are a function of the guide dimensions and the ratio of the cutoff frequency to the propagating frequency, and thrown in here is the intrinsic impedance. So making substitutions for all of those, we end up with, if you just do a direct calculation, you're going to get 0.0163 nepers per meter. And then that's basically equal to 0.142 dB per meter. So you can get this by taking 20 log of this, and then that basically gives you the relationship between the two. The dielectric losses are given by the following formula, and here's where the loss tangent shows up. Epsilon prime is approximated in a low loss dielectric as basically epsilon relative. So we can make a substitution square root of mu naught epsilon prime. We can substitute 1 over c for the mu naught epsilon naught part, and then the relative goes here in the numerator. So here's the speed of light showing up, and then the frequency here, omega. So we have a 2 pi up here that gives us the pi. The 2's cancel. Here is that ratio between the cutoff frequency and our frequency, and if you do all of that, you find that that is 0.0738 nepers per meter or 0.641 dB per meter. So in this particular example, the dielectric losses were higher, and that's fairly unusual. All right, now we want to move on to our first example of singular mode circular waveguide design. And so this is just a very simple problem. It asks us to design an air-filled circular waveguide such that only the dominant mode will propagate over a bandwidth of 10 gigahertz. So the first thing to do is to find the formula that relates the dominant TE11 mode and finds the cutoff frequency for that, and then we also want to find the cutoff frequency for the next higher mode, the TM01. So our band then needs to lie somewhere in between here. So for the TE11 mode, we have this formula, this constant times c over 2 pi a, where c is the speed of light. For the TM01 mode, we have the following formula, 2.4049c over 2 pi a. And so that gives us then an upper bound of the bandwidth. So if, oops,